Okay, we're going to talk about depth first search. With depth first search, what it involves on a graph is we start from a particular node and we explore all the other nodes and vertices that are connected by going from edge to edge. We are basically mapping out the graph when we do a depth first search. Now, the algorithm for depth first search can be a bit difficult to understand by itself. So what we're going to do is we are going to start by doing a simpler algorithm. We're going to develop the algorithm for depth first search on a tree, and then we are going to convert that algorithm to the point where it will work for a graph. So we're going to start with this graph that we want to do the depth first search on, and we are going to make it simpler. So what we're going to do is first we will start by labeling all of the vertices, so we know that which vertex we're talking about, and then we are going to turn the graph this way, and that's because we want our start vertex to be at the top, and then we are going to remove some of these edges to get the graph to be simpler, and we are going to remove some nodes as well and some additional edges, and finally this is what we are going to work with. Okay, now if you take a look at what we have here, what we have is a tree, a binary tree. Okay, so we're gonna develop the algorithm for depth first search on this binary tree, and then we're gonna go in the opposite direction we went in coming to this tree, and we're gonna add vertices and edges to get to the original graph. So this is what we are going to do. We're going to first develop the depth first search algorithm for this binary tree, and then we're going to introduce an edge. We're going to introduce the edge from node ABE, node Eve. Okay, so now what we have is no longer a binary tree because node ABE has more than two children. So at this point, we're going to change the representation we are using for the binary tree from the left right child representation to using an adjacency list. And the next thing we're going to do is we're going to introduce another edge. We're going to introduce an edge from Dan to Abe. Okay, and once we do that, you'll notice that we now have a circular path. And because of this circular path, we are going to see that our algorithm breaks down. Okay, and what that is going to do is it's going to force us to make changes to our algorithm to know which nodes have already been visited. So that means we're going to mark visited vertices. Okay, and then after we've done that, we are going to add additional nodes or vertices to our graph. We're going to add. Now, if we go to the previous slide, you are going to see that once we've done that, we have come back to this, which is the same structure as the original graph we were trying to do a depth first search on. So this is the approach we are going to use. In order for this to work, what we're going to do now is we want to implement this binary tree structure. And we're going to implement this structure in Python so that as we're developing our code, we will get to test our code as well. Now, as a binary tree, we will represent each vertex with a value and a left child as well as a right child. I know it's conventional if we are representing binary trees that we can also have a pointer to the parent node, okay? But for the purposes of this exercise, we don't need that. You'll notice that these arrows have a direction and none of them point in the opposite direction. So we are going to leave out the parent pointer for this exercise because it will not be necessary. We want to keep things as simple as possible. Okay, let's go over to where we're going to write our code, and we are going to write a class that will retain information on vertices as well as their state. So we're going to say class vertex. We're going to try to do it as simple as possible. This is our constructor. We're going to use the init method, and as always in Python, we pass self, and we're also going to pass a value. Okay. Now, obviously, we could also pass a left child and a right child at this point, but we're not going to do that. We're going to do it another way. Okay. The value is going to be the value we pass, and we're going to set the left child to none and the right child to none as well. Now, as I said earlier, we are not going to care that much about retaining information on the parent of a vertex because we are not going to need that information. Good. Now, with these, also we want to have a way of keeping edge information. Okay, so we are going to create a method which we're going to call set edges, and we are going to pass a child node of vertex and a right child node of vertex to this method. And we are going to retain that information for each individual vertex object. Good. Now, at the moment, this is all we need for our vertex class. And now we want to draw the tree. Okay, recall that this is the structure of the tree that we want to draw. Okay, we're going to create the nodes and set the edges. Now, to create the nodes, I am going to develop a standard for naming the nodes or the vertices. By the way, node and vertex means the same for the purpose of this exercise. Okay, vertex abe is the name of the abe vertex, the vertex with value abe. And I do the rest of the vertices as well. Okay, now that we have the vertexes, we are going to set the edges. And if we take a look at the binary tree, these are the 5 edges we need to set. So for vertex abe, the left child is Bob and the right child is Cass. For vertex B, the right child is Dan, there's no left child. For vertex C, the left child is Eve, the right child is Flo. What that means is we only have to call the set edge method 3 times. Once for vertex Abe, once for vertex Bob, once for vertex Cass. Because these other edges don't have children. And we're not setting the parent value. Okay, so for vertex Abe, we're going to set its edges, and its left child is vertex Bob, and its right child is vertex Cass. Vertex Bob, vertex Bob doesn't have a left child, so we'll put a none there, and its